I'd first like to express my sincere gratitude to Abushi and Dipankar, not just for having done all the work in organising this symposium, but also taking such good care of me for the days that I've been in Bangalore. And I'd also like to thank both the speakers. I think we've had a really very exciting lot of talks over these 2 days. I've certainly enjoyed it immensely and learned a lot. And also, and all the participants, particularly those who've made the journey from long distances. I really appreciate that. I've only prepared it's a very short set of remarks, and I will primarily be talking about the condensed matter and quantum information side of physics. Obviously there are things one could say about particle physics and cosmology, and in particular my own suspicion as a complete outsider is that sometime in the relatively near future we are in for a major revolution in cosmology connected with the problem of dark energy and possibly dark matter. But that's not my specialist area, so I won't say much about that. If we ask, as already of course been said, attributed to, well, whoever it was, Niels Bohr or Yogi Berra or whoever, prediction is indeed difficult, particularly when it's about the future. So it really is difficult to know the direction in which physics is going to go in the next few decades. But I think perhaps one can reasonably speculate about a few things. First of all, there are clearly right now some obvious issues which are not resolved, or certainly not resolved to most people's satisfaction. One very obvious one, of course, is can we get a room temperature superconductor? And I think while the recent results on the metallic sulfides have been extremely exciting and unexpected, I suspect that even if we can go to room temperature, as we may be able to do perhaps, if we're going to have to do it at 200 gigapascals, that's not going to be of enormous practical use. So I think a more interesting question is, can we get room temperature superconductivity under ambient conditions? And of course, the most obvious way of trying to do that is to try to figure out the mechanism, if that's the right word, of superconductivity in the cuprates, and then use that, if we can do that, perhaps we can use that as a clue as to either how to possibly improve the cuprates themselves, or I think more likely to find another class of materials which will be superconducting at room temperature. Another rather obvious, again, somewhat practical issue which we already see, I think, rather clearly, is to obtain an efficiency in artificial photovoltaic devices which is comparable to that which nature herself manages to achieve. In some sense, I find it rather surprising that, given, what is it, probably 40 or 50 years' work by now on photovoltaics, and a certain amount at least of understanding of natural photosynthetic processes, that we haven't done better than we are doing right now in that direction. Again, a more fairly obvious question which has come up in the last few years: can we build a working quantum computer? And I think in some sense that perhaps may not be a particularly deep question of as it were, pure physics. I mean, I suspect the answer is yes. The only question is it going to be so expensive to do it that in the end we decide it really isn't worth the candle, no, that we just simply feel there are other things we could be better doing with the money. I think that that could be the outcome. I think it's fairly obvious that the original the original justification, which was given by so many governments and so forth in spending enormous amounts of money on quantum computing, namely its possible use in quantum cryptography, or rather, what's the word, quantum code cracking, that's actually not a terribly good incentive. I think if the field of quantum computing is going to continue to flourish, what we've got to do is to actually find something we can do with a quantum computer, which is not simply a way of either doing something you can do with a classical computer faster or more securely or more reliably. I think we have to find some qualitatively new task which we wouldn't even think of attempting with a classical computer, but which can be done with a quantum one. And at least as far as I know, right now we don't have one. So that's, I think, a major challenge. One further question, I think, which is rather fascinating, is there some sense, at least, in which the human brain is working as a quantum computer? And here I do find that the recent proposal by Matthew Fisher that in some sense the at least certain elements of the brain could be working as a nuclear spin-based quantum computer. That's, I think, very fascinating speculation. It's fortunately, I think it's one which is going to be resolved, right or wrong, in fairly short order, because there's, in fact, a relatively straightforward experiment which I think would either act as a smoking gun for that hypothesis or definitively refute it. So I think that's something we're likely to learn in fairly short order. And of course, if the answer is yes, then that's extremely exciting and will have enormous implications. There are other issues which we know, which in some sense I think may require some kind of paradigm shift in our current thinking. My own view would be that although over the last, say, 60 years, although there have not been paradigm shifts in the sense of the historian of science, Thomas Kuhn, there have not been paradigm shifts comparable to, say, the Copernican revolution or the relativity or birth of quantum mechanics. Nevertheless, there have been a series of mini paradigm shifts, which, as Kuhn points out, are often invisible in retrospect, unless you look rather hard. One of these, for example, I think would be the Landau-Fermi liquid theory. Another might be the BCS theory of superconductivity, and again, the fractional quantum Hall effect. In each of these cases, I think, and I think it's particularly clear in the case of the Landau theory of Fermi liquids, what's happened is that people simply changed the kind of questions they were asking. Previously to Landau, the question had basically been, how do we start from the known interactions between elementary fermions, say, and try to do some decent calculation of the properties? Landau rather asked the question, okay, forget about that. How do we actually relate the observed properties of, say, liquid helium-3, normal liquid helium-3, and try to make sense out of them? And so, in many cases, I think progress in this field may require a certain degree of, in some sense, reorganization of the existing data. That, I think, is related to the question which a lot of people have raised. In the era of big data, is the human physicist likely to become obsolete? Well, I don't think so. I don't think that big data by itself is ever going to give us any real understanding. We've got to be able to organise it, or perhaps reorganise it. I think in this symposium, a rather nice example of that was given by Janendra Jain's talk on the fractional quantum Hall effect, where you had this enormous sort of plethora of data, and then it turned out a very nice idea. The composite fermion idea could really organise it and make sense of it. And I think there are a number of other fields where we really need to see if this can be done. One particular example, which I've been particularly keen on myself, is the theory of amorphous materials, glasses. Is it the case that, crudely speaking, each individual glass is just a system in its own right, and we simply have to look at the properties of the individual systems and try to address each one separately? Or is there, in fact, the same kind of overarching theory or perspective we can get, which we've had for many years in dealing with crystals? I would like to, I would hope that the answer is yes, but so far I think we really don't know. It just is something which requires a lot more work. Finally, I think there are, I think the really interesting areas, and this is of course true, not just of physics, but of probably most branches of science. The most interesting areas of research are not those in which we have well-posed questions and simply have to try to find the answers. The really interesting areas are the ones where we really don't know what questions we should be asking. And I think one can spot already one or two areas where this is the case. I personally, again, opinion with which I suspect a lot of people might disagree, but I would think that one example is the relation of the quantum mechanical description of nature to our own consciousness and perception. That's usually framed in terms of the so-called quantum measurement paradox. And sure enough, I mean, there certainly are important issues there. But I actually think that an equally important issue, which is not so often discussed, is what you might call the quantum preparation paradox. How do we, is it possible to describe the preparation of experiments, which clearly involves human actors and so forth, in quantum mechanical terms? That, I think, is, I find an extremely interesting question, and I suspect it's going to be more discussed in future years. Possibly related to that are questions concerning the arrow of time. It's not obvious that this question is one which is going to be resolved, as it were, at the level of condensed matter physics. I mean, it could be that, this is, I think, a rather common view, particularly among cosmologists, that the basic issue is really the relation between thermodynamics and cosmology. That is, crudely speaking, why did the universe start in such an extremely low entropy state? That could be right, and that, of course, in itself raises some interesting questions, about which, as far as I can see, at least the real heavyweights in cosmology can't agree. So it's already an interesting question, but I think there's also an interesting speculation that there may be some aspects of this question which, in some sense, are going to pop up at the level of condensed matter theory and possibly our own experience. For example, here's one crazy speculation, an analogy. If you have a set of iron atoms, say, we know that below the Curie temperature they tend to be aligned so that, I mean, borrowing all sorts of complicated domain effects and so forth, the spins within a particular piece of iron are going to point in one direction. But of course that's not entirely true. There are always going to be thermodynamic fluctuations in which small regions of the system fluctuate into the opposite spin orientation for a restricted period of time, and then go back again. could it conceivably be the case that although, as it were, on average, the arrow of time as we experience it runs in a particular direction, nevertheless, for restricted regions of space and for restricted periods of time, that could in some sense reverse. Now again, this is a typical example of a problem where, I mean, I can say those words, but I don't really know what specific questions to ask, and even less how we might actually do an experiment to decide if that were true or not. So I think this kind of question is very fascinating. I suspect one, and I think a lot of people speculate on this, that in the future, this kind of question is going to emerge in multiple forms at the interface between physics and biology and neuroscience and so forth. Well, that's basically as far as I can get, as it were. But I think one thing we've been reasonably certain is that almost certainly by the year 2100, if there is still a distinct discipline which we know as physics, which there may not be, it may well not be by that time, but if there is, then I think physicists in the year 2100 will be asking kinds of questions which in 2019 we don't even have the language to ask, let alone to understand the answers. So that's my contribution.
I suppose that's a fair enough thing. So may I ask Rohini Godbole to please come and say whatever you wish to.
This is the penalty I get.
Within 5 minutes. If,
This is the penalty I get for not giving the talk. So let me begin by offering my congratulations to Sir Tony Leggett.
May I say something before you begin?
Okay.
Rohini has been given the Padmasri Award, for which I think we should congratulate her formally.
Thank you. So I would begin by talking about the two subjects that were left out, namely the particle physics, cosmology, and astrophysics. Where is, at least from the point of practitioners, where do we think it's going? So for particle physics, we find ourselves in a very peculiar state. And I would like to quote from first lines of Tale of Two Cities, that it's the time of hope and it's the time of despair. In the sense that this is, let me just even quote, because I have it somewhere, yeah, that it is the best of the times and it is the worst of the times. And the reason it is best of the times is over a period of 70 to 75 years, there have been developments based on quantum field theory and relativistic quantum field theories and gauge field theories, the gauge symmetries, and that has become very clear and we have understood very deep things. And the culmination, of course, has been in the discovery of the Higgs boson at the Large Hadron Collider. And then everybody has said, is this the end of particle physics? There are, in fact, newspaper headlines in New York Times saying that it's the end of particle physics. What it is, actually, it's, and I mean, obviously I don't agree with it, that's why I use this, that it's the best and the worst. Why do I say it's best is obvious. Why it is worst is because we have found the Higgs boson, but we haven't found evidence of any other new physics which we had predicted, quote unquote prediction, that we might find it at the Large Hadron Collider. The predictions were based on a particular way of thinking about physics, thinking that, which is what 20th century taught us, that symmetries are great. So many of us were really looking at finding the ultimate symmetry, which is the combination of an internal symmetry and a space-time symmetry, which would have been the real beautiful thing. We haven't yet found it, that is supersymmetry. So in some sense, it's a cause for despair. But then you ask yourself, is it really the cause for despair? The point really is that the principle on which we made our predictions, which is called naturalness, that doesn't seem to be too good. In the sense that we said we expect the physics to be at a TeV scale, but there is a factor in front. And that factor in front actually is controlled by physics that we don't know. It's controlled by the physics at much higher scales, and we never knew how to compute it. And for people who say that LHC didn't find anything for us other than the Higgs, LHC has actually told us that natural principle in its simplest form is not the guiding principle. So that is actually one very important result that LHC has given us. And in some sense, for the first time, and this is what I will sort of end with 2 lines, that for the first time in the 80-odd years, particle physics theorists find themselves in a situation where they have to be led by data, by experimental data. Mind you, after the accidental discovery of the structure of the proton at the SLAC experiment, almost everything that was found, measured at any of the collider experiments was something that theories had predicted. So from 1968 till 2018, we are talking of a long period where, in fact, particle physicists kept on raising the bar, saying this is where you should find X, this is where you should find Y, and it has been found. Now, for the first time, I think we have to go back to the days when we had cosmic ray experiments and we had this multitude of particles and we had no idea what was the underlying principle. So in that sense, the experiments that will be still going on at the Large Hadron Collider are very, very important. But more than that, there are one set of experiments which are, if they happen, would be great, would be at a E plus E minus machine, which China is planning, and Japan is also thinking of building one. And why is that important? Because what we have learned is that the new physics is at some very large scale, physics beyond standard model, and that should exist not because I like it or theorists think that we should have it will be aesthetically pleasing, not because of that. Because we have issues such as baryon asymmetry. We have issues of dark matter, and we have simply no understanding of those issues in our knowledge of particles. So if dark matter is particulate, we don't know the candidate. So in that sense, these are questions that need to be answered because we are physicists who want to answer experimental facts. So therefore, one way in which theorists think of doing this is that the large-scale physics is integrated out and added on to the known Hamiltonian as an effective field theory, effective additional operators. And there is nothing wrong in it because weak interaction theory started its life as Fermi's theory of beta decay was an effective theory. So the days for particle physicists are days of effective interactions, and more important than that, they are days of close interaction with cosmology and with the experiments in the sky. So basically, experiments just at the colliders are only part of the story, and there is deep connection now between what dark matter experiment detectors do in some lab underground and what Large Hadron Collider tries to do. And I think if not the borders between different disciplines like physics and biology that you are mentioning, I certainly think for particle physics or this related physics, the interaction, the boundaries between cosmology, astrophysics, and particle physics are very slowly getting very merged, because what we have found is that the laws of physics that we have studied at the collider actually have implications to things that are happening and happened in the early universe. So in fact, to me, it's the most exciting time to be a particle physicist, because there are first time when we will have data which we would try to interpret in terms of, there is going to be a paradigm shift. That is sort of clear now. That the basic paradigm of quantum field theory and symmetric quantum field theory is perhaps going to require some changes. So that's all I would say.
Okay, thanks a lot, Rohini. May I now request Apurva Patel to say a few words, if you would?
Well, actually, I wanted to show a couple of slides.
That's too late, yeah.
Can
Okay.
somebody else talk? I will.
Usha, would you like to say a few words?
So, again, thanks for this opportunity. I thought of saying something about this meeting being condensed matter as well as quantum physics as such foundations. So this, in the present scenario, we are, quantum foundations is finding a lot of revolutions in terms of single system experiments. So I wanted to say experiments in condensed matter which are doing, I was talking to Deeptiman today, that is generation and manipulation of quantum entangled electrons of a Cooper pair by splitting them into two branches. And they are testing non-locality at that level. These are some experiments. And there are experiments at the nano level, nanoparticles. They are finding rigid dumbbells at the nano level and doing experiments which are to find classical and quantum. Those are all possible because of this kind of a revolution today. And I think it is quantum foundations, measurement problem, and quantum biology, because I do get, that is, there are experiments which are trying to do the photosynthesis, photo-harvesting complexes in terms of quantum physics, and there are some theories which uses the Leggett-Garg inequalities to see whether the photo-harvesting complexes can violate them. Can they find some loophole-free kind of a Leggett-Garg inequality in complexes like that? And there are such progresses being done, and also in magnetic aviation, where they see the NV-center diamonds, where they can see the transition between triplets and singlets, which Professor Bhaskaran was also mentioning. So these are the experiments which might guide us towards the correct thing, all that what Professor Leggett told us. So these things are happening, and we should be happy to be in this scenario and to look forward to what is happening in foundations.
Thanks. Thanks. Vikram Soni?
Well, the first thing is that I'm very happy to be here at Tony's 80th, because we have a long association. And I think when I was at Sussex, actually we did some work on topology for which you were responsible. And the same work actually led to the first solution of something called the sphaleron, which you don't know about, because by that time I had gone to Madras. You were still in Sussex, but Mrs. Thatcher came in and suddenly you moved to Urbana. But also at that time I told you that with Bhaskaran in Madras, we actually looked at what is now called BES, BCS. What did we call it? Permutation symmetry breaking. So there were many things, parallels which were happening. It was serendipity. It had nothing to do with anything of this kind. And then after that, I railroaded Tony into start thinking about the planet, which I do not know at this moment of time, but we'll have something to say about it tomorrow maybe. I think this seems to be the overriding theme. So let me go a little bit beyond what we are talking about. We are too terrestrial in what we are talking about. I think one of the places which everybody has talked about is cosmology. The dark energy problem, you talked about it, the dark matter problem. These are cosmological problems. But there are other problems in astrophysics, where there's an enormous system, I'm going to talk a little bit about it tomorrow, which is actually a condensed matter system. It's the state of matter at very, very high densities, 5 times nuclear densities, in a neutron star where you have, very strictly speaking, a very strong degenerate Fermi sea. Maybe of neutrons, maybe of quarks, we don't know. It's an open thing, and the only data that you can get on it is going to come out from what is coming out of that star, the radiation. So you have to start at in the interior and you'll work your way out. So there's a huge mine over there of all kinds of physics to be done, including the plasma physics. The second thing is that people forget. I mean, I've always got hold of Bhaskaran to start working on this, but he never does that. Is that we have fields of 10 to the 15, 10 to the 16 Gauss in magnetars, which are the highest fields in the universe, highest magnetic field. And we have a system on the crust of a neutron star, and what happens to that crust, I'll be talking a little bit about it tomorrow, is a very interesting condensed matter problem, which actually is responsible for the kind of radiation that you see coming out of these stars. So there are a lot of very interesting problems which are there in astrophysics, not just cosmology. And these may be dirty systems, but stars have been around for a long time. And you do come out sometimes with great new insights on stars. I'm not going to venture into fields of quantum mechanics. You've probably had 2 days of deliberations on that. Another thing I wanted to say is that one of the things which we tend to forget, which particle physicists, or rather, particle physicists is a wrong word, field theorists think about, or string theorists even, is the extra dimensions. Are they? Or are they not extra dimensions, and what are the consequences of them? And then there's the eternal question of dark matter, or whatever induces you to think about, are there only 4 interactions in nature, or are there more interactions in nature? So, without taking too much more time, all I'd say is that it would have been really nice if I couldn't have come earlier because I was just not so well, to talk about some of the reminiscences. But these are some of the issues that we have. And the issues, therefore, they span a much bigger field than just cosmology. They're all over the place. And I think that physics at the moment is, as you were saying, it's a very open game. I don't know about 2100, but I think in the next 10 or 15 years or decade also, something's got to give. All the best.
Thank you. Thank you, Vikram. Apurva, you 5 minutes.
First, let me again wish Tony all the best for the coming years. And I wanted to report something for the future because that is one of the items on the discussion list. And I have decided to show you some things in which I have gotten involved to some extent. There are several other people in the audience who are also involved, but it's a topic of interest more general than that, and that is the subject of quantum technology and what is going to happen worldwide, and on top of that, what we can do about it in our own country. And there are a lot of things expected because of essentially technological developments, and these developments will use quantum features essentially in the dynamics of the processes which play the part, and these features are the usual labels: superposition, entanglement, squeezing, and tunneling of quantum states. And the essential part is that without these features, the devices will not have the same power as they will have when these features are included. So what is expected is in some chronological guess. The first things which has already started happening is improvement in sensing and metrology. This is a gradual process, but all our measurements of space, time, energy, charge, etc. are going to get more and more refined to higher precision, and those instruments will help in a lot of new devices. Things which are big instruments now may become handheld devices in the future. And that is the kind of change we may experience. The next step is in communication and simulations. A lot of ingenuity is needed in this to think of new devices and new paradigms where even though our quantum devices may not be perfect, you may be able to do something non-trivial. And that is a big area of investment from many research institutes as well as private companies. The third thing which will happen is some feedback on the foundations of quantum theory, and the leading candidate for is the understanding of quantum measurement. The projection postulate is not going to survive as it is. It's a discontinuous process, and we don't really like discontinuous processes in physics. So the new measurements or the higher precision afforded will actually replace those projection postulates by some kind of quantum trajectories. That is one of the labels which is being used. These are non-universal features of the dynamics, but certainly they will help us understand what will happen between the system and the apparatus every time you make a measurement. It's an open question for a century, and now I think the technology is going to give you the escape from that, assumption or guess, which is not really a dynamical equation. And finally, we will reach the topic of computation, which will necessarily involve error correction, and that is the place where we will really learn how to design and control quantum systems. So that is the part which converts science and technology. It's not merely a question of observation, but it's a question of design and control, and a lot of engineering will develop together with this particular part. So this is a rough roadmap, and it's a kind of moving target because classical devices are also going to keep on changing at the same time. And the question is that many places worldwide have put up a roadmap, what will happen 10, 15 years down the line. We really don't have such a clear map in India, and the point is, what do we want to do about it? And so this is what has happened after a lot of arguments and heartburn with discussions with government agency. There is a project labeled QUEST, Quantum Enabled Science and Technology, which the Department of Science and Technology has more or less approved. It consists of 51 proposals distributed over 4 different themes, and the recommended funding for 3 years is 300 crores, which is about $40 million. And we are optimistic, or rather that is what we have been promised, that it will start this year. And if you are lucky, something might happen before 31st of March. That date has an Indian significance, so that's what I'm mentioning. And the next step, which has to be planned in parallel, is something which I would call the National Mission on Quantum Technology, which will take the successful outcomes of QUEST and fund them on a much larger scale in some sense of a mission mode effort. And in principle, various parts of government and bureaucracy have looked favorably about such a scenario, and it has to be set up so that it is free of lot of this bureaucratic jugglery. So we want to set it up as if it's an independent mission supported by all different government agencies, so we don't have to keep on going and asking them for money every time. We will have an overall allocation for the whole project. And I am sort of involved a little bit in terms of what to do for this national project, and we hope that something will happen. So that was what I wanted to report. Thank you very much.
Thank you, Apurva. There's one more speaker I would like to invite, Muhammad Nazri bin.
Okay, hi. I'm Nazri. I think this is my first time in India. I'm from Malaysia. Okay, I got an invitation from the organizer, and then I think personally from Tony. Tony came to my university in 2013, and I'm the officer in charge of Tony. It's about 6 years ago. Yeah, and then it's a great pleasure to be here because this is all the big name of physicists. I just want to share my, I don't know, I got my poster here. This is my talk. I give a talk to the student at Malaysia since 2016. I think Tony know about this one. And then I asked Tony to write something here. So this is my 4th year. I do it free of charge. Across Malaysia, about 340 schools involved. And part of this, 10 is from Indonesia. So I do it about 3 hours to visualize about the beauty of physics to the school student. Because in Malaysia, physics is a second-class subject. Okay? They score A in the secondary school, and then they move to engineering. So nobody like physics because, you know, physics, they're always talking about pendulum. Okay, always about the pendulum, and that's it. So I have about 3 hours to talk about physics, the beauty of physics for the secondary school student. But in 2017, I start for primary school. That's very challenging because I want to talk about physics to the primary level. So what I do is I put all the videos, and if the student happy, they laugh. So I hope they love physics. So that's, I try to do it. And then in 2018, last year, I start for physics teacher. I finished 3 states at Malaysia for the physics teacher. And part of my talk about the beauty of maths, I looking about the pi, the number pi. So I start to do the competition among students in Malaysia. I start in my place to memorize pi, because the world record now is from India, 70,330-digit pi, about 17 hours, 40 minutes. For last year, I managed about 322 students, and the record is 753 digits of pi. That's a Malaysian record. And I sent all the names, and now Malaysia is the second after United States in the pi world ranking list. So this year we try to do it again, and the next year we try to do it in the national level. So I think that's my contribution for the 20th century physics, because we want to have a talent of student. And I hope from my talk, there's 1 or 2 students who love physics from secondary school or primary school. That will change a lot the scenario in Malaysia. That's it. Thank you.
Thank you very much. I made a mistake. I apologize. There's one more speaker, Dr. Pragya Shukla from IIT Kharagpur.
I'm happy to be a mistake, but anyway, I decided to. Okay, I think there are leaders of the community sitting here, and I'm not the right person to speak about future of physics. However, I do have some opinion about it, and I think nature is going to surprise us. We are not going to, right now we can predict this is going to be the science we are going to be doing in next 50 years or so, but nature is going to actually change what we are going to do in next 50 years. But still, looking from today's point of view, I think there are some things which have always excited me, and talking to many people, many experts, I think one thing I'm sure, I mean, you may think this is a surety of a fool, I mean, who doesn't know much, ignorant mind, but I'm sure you will not find answers of all these questions which are prevailing today in science within existing theories, and you have to go beyond quantum mechanics. So it's not only you need quantum technology, you have to go beyond quantum technology, and I think quantum physics will be like 2 sides of a coin, like classical physics one side of coin and quantum physics on, and another big theory will encompass that. Okay, but after that, one thing which I'm very keen about in my present state of mind is physics of consciousness. I think this is one of the most important topics which very soon going to provoke us. There are so many questions which we have been ignoring for practical reasons because we don't even understand basic things, but very soon you will not be able to ignore. And then psychophysics, which I didn't know this is called psychophysics, but now I have learned that this is called psychophysics. I think we are having psycho-generation. The present generation is psycho-generation, and this is not a matter to laugh. Because we have so many mental issues, so many, you understand what I mean by mental issues, and I think, this is my personal belief, a lot of it has to do with physics. That means engineering, electronic revolution, technological gadgets which are so easily available, all the time sleeping, awake, all the time are next to us, mobile, computers, and they are affecting us. Radio waves are affecting our brain. Maybe our brains have already got changed. Neurons have already got affected. And I think we have to spend a lot of time on psychothinking. I have learned, I have been very lucky. Tony came to, just 1 minute I'll take. How I got to know Tony, it was because we were having this Golden Jubilee celebration in Kharagpur, and Tony was invited. That was before his Nobel Prize. And fortunately, it was before Nobel Prize because no crowd was following him. So he was sitting alone in the physics department. And of course, you know IIT Kharagpur, people, doing other things. So Argo left him with me, and I started asking him, what about quantum correlations? So he was telling me about this cat dead and cat alive experiment. So he was saying the question is, what is the intermediate state? And as usual, just to provoke him, I said, maybe a ghost. And I thought he's going to reprimand me, he's going to shout at me like, what is this nonsense? But he was, maybe. Then I knew this is the person I must work with. And the moment he gets the Nobel Prize next year, fortunate for me, I write to him, sir, you are the person who deserved the Nobel Prize. Do you remember, Tony? Yeah, so you are the person who deserved Nobel Prize because you have a very open mind to real problems in physics, real problem in nature. And therefore, I would like to have some opportunity to work with you. So then it started. And I have been bothering him every time I meet him about consciousness. He always evades the questions. But okay, with that, I'll thank you.
Thank you so much. Thank you. So now I suppose everybody who didn't have a chance to give a formal talk has had the chance to speak here. Last one to speak. May I now request Professor Ramakrishnan? I'm here to listen. No, but no, sure. Rafael Sorkin, please. Just anything you may have to say about the future or the proposals given by Tony or anything else you want.
And I see it's getting late and people are tired, at least I know I'm tired. So I'll try to concentrate only to be very brief and to concentrate on things that haven't come up so far in any of these forecasts or perspectives. And of course, it's my first love, quantum gravity. We haven't heard anything directly about that yet. I just want to say provocatively that I think we may already have experimental evidence of quantum gravity, and that's in the so-called dark energy. I think I won't go into the particular theoretical prediction that some of us have made, but we should know within 2 or 3 years whether it's thrown out or whether it succeeds. And that prediction is based on an assumption of spatiotemporal discreteness, or as you might call it, atoms of space-time. And when you have atoms of space-time, that is when you have discreteness, and if you still preserve Lorentz invariance, which this particular theory does, then you're driven to non-locality. This is non-locality, even at a classical level, let's say at a pre-quantum level. We've heard a lot about non-locality in quantum theory, but I'm talking about something even in some sense more fundamental. So these are the places that I would hope for some progress, some of these questions to be settled in the not too distant future. And let me end, I'll just throw in the word, just to be as iconoclastic as I can, non-unitarity. I think this will also follow inevitably from the kind of framework involving spatiotemporal discreteness that we're working on. And it's interesting, no one even addresses the issue of unitarity. It's kind of a religion as far as I can see. If you ask people what are the experimental bounds on unitarity violations, you just get usually a blank stare. Well, we know the probabilities add up to 1. There can't be any bounds. There can't be any non-unitarity. Of course, as maybe, and I'm not sure if Spenta covered it in his talk, but there's evidence already a long time from black hole physics for some kind of non-unitarity, although the string theorists don't want to believe it, want to do away with it. So let me finish. So that's kind of my perspective in the more quote-unquote practical sense. Let me finish with slightly more philosophical questions. And this is that there's an interesting, I hyped a little bit on non-locality and discreteness as a result of discreteness. There's some hope, I think, this leads us to some hope of resolving an interesting disunity in quantum mechanics, which is not often remarked on. What is often remarked on is a disunity in physics, which comes from not being able to yet marry quantum mechanics with general relativity or the theory of gravity. But even within quantum mechanics, I think there's an interesting disunity, which I'll just summarize by saying that at the level, at the kinematic level, it remains local. At the dynamic level, it's non-local. And this is a very bad disunity. It should be resolved one way or another, and it blocks a further unification, which I'm not claiming is imminent, but someday physics should resolve the split between kinematics and dynamics, which shows up so clearly, say, in the path integral, where you have the paths and then you have the amplitudes, and the amplitudes come from somewhere outside. So I would hope that if we focus on this particular aspect of the disunity, the locality versus the non-locality on one hand, locality on the other hand, that may be a clue in unifying the two more thoroughly, at least hopefully to unify the non-local. I think it'll be resolved in the favor of non-locality, of course. So I think maybe a moral for the coming period is that we have to learn to live with non-locality and to incorporate it in our theories in a more fundamental way. So.
Thank you, Raman. Maybe I should now ask some of the youngsters to come and say something about their experience of this conference and what future you see. They are the future.
Okay, I'm Surya from RRI. Okay, I wanted to say that when we're talking about future of physics, we're talking about the vast majority of open problems that somehow have been told to our generations. Like much of the problem that we're seeing now about why gravity doesn't work with quantum mechanics is pre-our era. While you're learning, there's a big hurdle that when we are trying to solve those problems in our graduate studies, what happens, there is very little time to understand and appreciate the problem and then go for a solution. It's like, okay, this much work has been done, and therefore you proceed from here. There's no time to absorb the problem. So there are not problems that necessarily appeals to this generation because they're not their own. So there's a very little chance that those problems that you're talking about now will get solved in the near future unless we change the way the young generations are being taught. So maybe there are some new areas of physics which will be explored, and people will come up with their problems of their own, which they feel, and therefore they'll find their own way. The structure that we have in today's generation is mostly you're assigned a problem, there's hardly any time to appreciate the problem and find your own direction. I think that is very, very missing, and unless that, I think those grand problems will be very, very difficult to solve. Maybe students can go out of their way to find new problems and try to attempt that, but that's my concern.
Thank you. To anyone to come and say whatever you wish to.
Maybe I just...
Yes, Shashank, yeah.
It is more an appreciation than a comment. We have...
Come here and say, so that everyone can hear.
There is a group of people who have worked maybe for 20, 30 years on tests of unitarity at high energies. And the most prominent of them is probably André Martin, but some of us have also contributed to this effort. Now, typically what happens is that occasionally we have stumbled into results which appear to violate unitarity. One of them is that we found with Virendra Singh a bound on the difference between sigma total pi minus p and sigma total pi plus p in terms of the square root of the charge exchange cross-section, namely the cross-section for pi minus p going to pi 0 n. And this bound is apparently violated by the present trend of the data. But our belief in unitarity is strong, and we feel that since our bounds are asymptotic, maybe future energies will resolve this problem. Another thing I should say is that one of the fundamental bounds on the total cross-section, which is due to André Martin, namely the Froissart, which we call the Froissart-Martin bound, is based basically on, the main hypothesis is unitarity. But there is no evidence that that bound is violated. There is evidence that that bound is saturated at present energies.
Thank you very much, Shashank. Chandan, would you like to say something? Anybody else? You? Madam? No? Martin?
I wanted to say some words about quantum computers and their chief application right now, Shor's algorithm. So what it looks like, they might have a huge impact on our society long before they are built. Because if the whole communication that we are doing right now keeps being done as it is, nobody is secure. So basically every single text message, email, bank transfer, a phone call, everything will be able to, everything will be possible to eavesdrop. But what is really interesting is now that there are some countries, the US for example, who download, not really download, they record the whole communication done by internet. The US have this so-called Utah data center where they don't exactly say what it is, but it's basically a huge hard drive which does nothing else but store communication. So if in 10 years' time the US gets a quantum computer, they will know every secret we have now. So if we are able to have a, say, quantum cryptography in 5 years or post-quantum cryptography in 5 years, everything until that 5 years will be known. And also, it's probably not only the US, probably there are some other countries that are doing this. And imagine these countries being able to blackmail every single politician. Because if you're a politician, I don't know about India, but I know about Europe. So it's unlikely that all of them are perfectly clean. But even if half of them did something that they are ashamed of. Not really something very bad, but something a little dodgy. They can be blackmailed. Imagine a country being blackmailed by 3 foreign powers at the same time. It's an apocalypse. So, and there's nothing we can do about this, because if quantum computers are built in 10 years, all the secrets which are secrets now, in 10 years will still be dangerous. So, and the quantum cryptography will not be here really soon. So the only solution is so-called post-quantum cryptography. These are classical protocols which are secure against attack by Shor's algorithm. We don't know about other attacks, but at least this one attack they are secure against, and we should adapt this as soon as possible. More and more agencies realize this, and they are starting some programs to find it and so on. But even when we have new standards, we will need tens or hundreds of thousands of engineers to change every single system in the world to have these new cryptographic standards. So it's a huge problem, and I believe that like this blackmail apocalypse is impossible to be averted. We can only soften the blow by adopting post-quantum cryptography as soon as possible. It's the sensible option. And then what will happen is that whenever new protocols in cryptography are adopted, they don't work. And we're looking at a huge hacking problem all over the world with new technologies which are not ready yet being hastily adopted. So we're into some big problems.
Rafael.
I'm not going to say anything new, but I want to underline something which I think Rohini said, which is two profound things, that some of the principles that guided the development of particle theory until now seem to be breaking down, and we really need to take those on board and understand what to use as a guide henceforth. The two being, on the one hand, what's called naturality, which is a little hard to characterize, but let's say there should be no fundamental big numbers, if you want to say that, and the other one being symmetry.
Thank you. Well, with that, I think we can bring the session to a close. People are hungry, but as the chairman and as a very old man, more contemporary with Tony, I would just say one or two words. And first of all, to thank Dipankar and Urvashi for giving me this wonderful opportunity to come here and chair this very important session. But physics-wise, I would just like to say that as one grows old, one realizes that philosophy is very important. And I have a feeling, and I'm sure I can back it up, that most of our physicists are being trained in a fashion where they are completely ignorant of both philosophy and the history of science. And I think it's very important that unless you understand the historical way in which a concept came and why that change was necessary, you don't really understand that concept. And you also don't understand what are the limitations and how to proceed further. Other things that bother me was triggered by what Bhushan Ayu asked me over lunch yesterday. He said, does a single photon, what happens, how do you see a single photon, with one eye or two eyes? So I thought he was joking, but he was serious. What he meant is the two eyes are detectors, and only one of them can detect a quantum, which is correct. And the two eyes will detect randomly. But then I said, I agree with that part of the statement, but I do not agree with your statement about what we see. Because what we see is something which is constructed by the brain from the stimulus received from the eye. This is something that has been bothering me for a long time, and our deep poets knew about it. And so the question of, I don't know whether to call this consciousness, because I don't know what is consciousness. Everybody has his or her own idea of what consciousness is in. I know the brain, because it's a very physical thing. I think the mind also is like that. But if you ask me about consciousness, about aesthetics, and so on, I really don't know. And therefore, it's very important to also think about such things. You know that I'm interested in many things, and I was reading a play by Bernard Shaw recently, because I'm directing that play in Kolkata. And it's called The Doctor's Dilemma, in which it's brilliant satire on professions as a whole. It's that all professions are actually cheating the laity. And yes, and then there is this woman who's been let down by a doctor, and she says, "Oh, to me, you were just bones, and just a physical thing, and I operate." She said, "Okay, you operate on me and find my conscience." I think it's brilliant. So I think it's time for us to also think about deeper issues of life, if I may put it that way, because ethics comes from somewhere else. Einstein himself said that science tells you what to do and how things work, but it doesn't tell you what to do with that knowledge. That comes from somewhere else. That's ethics, and that is ingrained in a healthy society, he said. And he also went this far to say that these traditions are enshrined in societies by revelations in great people. I'm almost verbatim quoting him. And these revelations come, God knows from where. Inspirations in music, poems. I just read a poem by Feynman sent to me by my friend Siddhartha Sen. Wonderful poem. I never knew Feynman could write such poems. So poetry, philosophy, human relationships, these are very important. And if these, I feel that science ignores them, because science as we know it, cannot deal with these complexities. So temporarily at least, science dispenses with them. And sometimes people go to the extent of declaring them to be illusory, folklore. Now, I have a feeling now that it's dangerous. This sort of philosophy is dangerous for society. And so we ought to have a more holistic education and a more holistic philosophy, so that we can live more peacefully and more satisfactorily. Don't mind my saying these things. I'm an old man, so forgive me if I have gone beyond my limit. Thank you very much, and good night.